Scientists just watched darkness move faster than light. Confirmed. Published in one of the top scientific journals on Earth, March 2026. A piece of darkness inside a beam of light hit infinite speed, then vanished. The whole thing lasted 3 quadrillionths of a second, and a team of physicists caught it on camera. Einstein's rule says nothing travels faster than light, 186,000 miles per second. Absolute limit. Everyone knows that, except the universe just showed us the fine print. We're going to cover how this actually happened, what it means, why warp drives just got more real, and what the speed of light is actually protecting. If you enjoy it, subscribe. Buckle up. We begin. You have heard it 1,000 times. Nothing travels faster than light. It is the most famous rule in all of science. Teachers say it. Movies use it. Scientists repeat it like a law carved into the universe itself. And for over a century it has held up. Every experiment, every measurement, every test, the rule survives all of them. But here is the thing almost nobody tells you. Einstein never said, "Nothing moves faster than light." That is a simplified version, a shortcut. And like most shortcuts, it leaves out the part that actually matters. What Einstein said in 1905 was far more precise. His special theory of relativity established that no mass, no energy, and no information can travel faster than light in a vacuum. Those 3 things: mass, energy, information. Everything else the rule does not cover. That distinction sat quietly in physics textbooks for decades. Most people skipped past it. Seemed like a technicality. It was not a technicality, it was a door. Think about a shadow. You stand outside on a sunny day and you wave your hand. Your shadow moves across the ground in front of you. Now imagine doing that same thing, but your hand is a powerful laser and the wall is the surface of the moon, 240,000 miles away. You flick your wrist. The laser dot sweeps across the lunar surface. That dot can move faster than light. Easily. With a flick of your wrist. Has anything broken? Has Einstein rolled over in his grave? No. Because the dot is a geometric effect. It carries no mass, no energy, no information. Nobody on the moon receives a message. Nothing physical travelled from one place to another at superluminal speed. The dot is just the intersection of a beam and a surface, and that intersection can shift as fast as the geometry allows. This is the exact distinction that Einstein's rule is built on, and physicists have known about this category of exceptions for a long time. The problem was that knowing something exists in theory and actually watching it happen in a lab are 2 completely different things. For 50 years, physicists had a prediction sitting in their notebooks, a specific type of dark point, a tiny hole of 0 amplitude buried inside a wave structure, could theoretically accelerate past the speed of light right before it collides with another dark point and disappears. The math said it was possible. The math said the velocity could technically reach infinity. Infinity. Faster than infinite speed. At the moment just before annihilation. Nobody had ever seen it. The timescales involved were so short, and the spatial scales so small, that no instrument on Earth could capture it. Then the instruments got better. In March of 2026, a team at the Technion Israel Institute of Technology published a paper in one of the most respected scientific journals in the world. They had built a microscope system precise enough to catch the event, and they watched darkness move faster than light. Confirmed, measured, on record. The universe had been hiding the fine print for over a century, and now someone finally read it. What they found was stranger than most people expected, because the dark points that broke the speed record are not particles, not beams, not rays of anything. They are absences, holes in a wave where the signal drops to exactly 0. And those holes move in ways that should feel impossible. How they found them, and what these dark holes actually are, is where this story gets genuinely strange. 186,000 miles per second. Write that out. 186,000 miles every single second. Light travels from here to the moon in about 1¼ seconds. It crosses the entire width of the United States in roughly 1/100th of a second. It circles the whole Earth 7.5 times before your heartbeat finishes. That number is not just the speed of light. It is one of the most fundamental constants in all of physics. Scientists call it c, and they have measured it so many times with so many instruments that we now know it to 11 decimal places. It does not change. It does not vary. Everywhere in a vacuum, light moves at exactly that speed. But where does that number come from? Why that speed, and not faster? Why not slower? Here is what most people miss. The speed of light is the speed of causality. Causality means cause and effect. You throw a ball, it breaks a window. The throw is the cause, the break is the effect. The effect cannot happen before the cause. That ordering, cause before effect, is baked into how the universe works, and the speed of light is the rate at which cause and effect relationships can spread through space. Think of it like this. Every event that happens sends out a ripple of information. That ripple moves outward at the speed of light. Anything inside that ripple can be affected by the event. Anything outside the ripple cannot know the event happened yet. If something could travel faster than that ripple, it could carry information backward. An effect could arrive before its cause. Time would stop making sense. A universe where cause and effect lose their order is a universe where nothing can be predicted, nothing can be explained, and nothing we experience as real would hold together. So the speed of light is the universe's way of protecting logic itself. Einstein figured this out in 1905 when he was 26 years old and working as a patent clerk in Bern, Switzerland. He was not working in a fancy lab. He was sitting at a desk reviewing other people's inventions and thinking about what would happen if you could ride alongside a beam of light. What he found was that the laws of physics would collapse. Electricity and magnetism would stop working. The equations that describe how light moves would break. The only way to keep physics consistent was to accept that light's speed was the absolute ceiling for anything carrying mass, energy, or information. What he did not say, and this is the critical part, is that nothing in the universe could ever appear to move faster. Geometry can move faster. Patterns can move faster. Mathematical features inside a wave can shift faster. Shadows can sweep faster. The expanding boundary of the universe itself moves faster, and that does not violate a single equation. The rule is surgical. It protects one specific thing: the ability to send a message, carry energy, or move matter faster than the universe's causal speed limit. Everything else is still on the table. Scientists have spent decades cataloguing the things that technically exceed light without breaking physics. A laser dot on the moon, the edge of the observable universe racing away from us. Certain wave patterns inside specialized materials, and in 2026 they added a new one to the list. A dark point inside a wave, a phase singularity, accelerating to infinite speed in a laboratory in Israel. But to understand what a phase singularity is, and why it moves the way it does, you first have to understand what nobody predicted for 50 years, and why it took this long to find. Somewhere in the 1970s, a physicist wrote an equation. The equation described a strange feature that can appear inside a wave, a point where the wave's amplitude drops to exactly zero, a tiny hole in the wave structure surrounded by a spinning vortex of energy. The physicist called it a phase singularity, and buried in the math was a prediction that most people glossed over. When two of these singularities get close enough to each other, they start to accelerate. The closer they get, the faster they move. Right before they collide and cancel each other out, the math says their velocity climbs toward infinity. Infinity. An object with no mass reaching infinite speed in a lab setting. The physicist wrote it down, published it, and the scientific community mostly filed it under interesting, probably unprovable. because the timescales involved were absurd. The whole event from acceleration to annihilation unfolds in less than 3 quadrillionths of a second. 3 quadrillionths. In that span, light itself travels less than a millimetre. No camera in the 1970s could see it. No camera in the 1980s could either, or the 90s, or the 2000s. The prediction sat in physics literature for roughly 50 years, about as long as the internet has existed. A theoretical footnote that nobody could touch. And the frustrating part was that the physics was completely sound. This was not a fringe idea. Phase singularities are real, well-documented features of wave physics. They appear in light beams, in sound fields, in ocean currents, in quantum systems. Physicists work with them regularly. The prediction that they could go superluminal under the right conditions was built on solid mathematics, not speculation. It was just untestable for half a century. Then, in the early 2020s, a professor named Ido Kaminer at the Technion was working with a new generation of electron microscopes. These were instruments designed to image materials at the nanoscale, the scale of individual atoms. Kaminer's team had been pushing the technology in a specific direction: ultra-fast imaging, capturing events that unfold in femtoseconds, quadrillionths of a second. And one day, the team asked a question that had not seriously been asked in decades. Could the technology finally be good enough to catch the singularities? The calculation said maybe. If they used the right material, one that slowed light dramatically, the superluminal event would happen at lower absolute velocities, making it measurable. If they paired that with the new electron interferometry method the team was developing, they might reach the spatial resolution needed to resolve features far smaller than the wave itself. It would require running the experiment hundreds of times, capturing snapshot after snapshot at slightly different moments, and stacking the images into a sequence precise enough to track the singularities frame by frame. Ambitious, technically brutal, but physically possible, they decided to try. What happened next confirmed the 50-year-old prediction completely. And along the way, it produced something nobody had seen before: a direct image of darkness moving faster than light. But before we get to the moment of confirmation, we need to understand what a phase singularity actually is. Because calling it a dark point in a wave barely scratches the surface of how strange these things really are. Picture a wave on the ocean. It has peaks and troughs. It moves forward. If you drop 2 rocks into still water at the same time a few feet apart, each one sends out a ring of waves. Those rings expand outward and eventually cross each other. Where they meet, something interesting happens. At some points, the peak of one wave lines up with the peak of the other. They add together. You get a taller peak. At other points, the peak of one wave meets the trough of the other. They cancel. You get flat water. Those flat points, the places where the 2 waves perfectly cancel each other out, are called nodes. The amplitude at a node is exactly 0. The water there is completely still, even though waves are passing through on every side. Now take that idea and apply it to light. Light is also a wave. When multiple light waves overlap, they interfere with each other, creating regions of brightness and regions of darkness. Most of those dark regions are just simple nodes, flat spots in the pattern. But sometimes, under specific conditions, the waves create a special kind of dark point. At this point, the wave amplitude drops to exactly 0, and the wave's phase, the part of the cycle the wave is in at that moment, becomes undefined. The math has no answer. The phase at that point is not just low or ambiguous, it literally does not exist. That point is a phase singularity. Surrounding that singularity, the wave does something remarkable. Instead of just passing through normally, it swirls. The phase rotates around the singularity like water circling a drain. In the field of optics, this is called a vortex, because the wave pattern spirals around the central dark point. These optical vortices are real, they are measurable, and scientists have been working with them for decades. They appear in laser beams deliberately designed to carry them. They appear spontaneously in random light fields. They are more common than most people realize. What makes them unusual is their topological nature. A topological feature is one that cannot be smoothly removed. You cannot gradually shrink a vortex out of existence. You can only destroy it by colliding it with another vortex that spins in the opposite direction. The two singularities meet, cancel each other's spin, and both vanish simultaneously. That moment of collision is where the 50-year-old prediction lives, because as two singularities approach each other, they do not glide smoothly together at a steady speed. They accelerate. The closer they get, the faster they move. And in the final instance before annihilation, the velocity climbs toward infinity. Infinity is not a speed. It is the absence of a limit. And for a split second, these dark holes in a wave structure have no speed limit at all. To be precise about what this means, the singularity itself has no mass, no energy, and carries no information between 2 points. It is a geometric feature of the wave pattern, a location defined by math. Its motion is the shifting of that mathematical location, not the transport of anything physical. This is why the speed limit does not apply. But to see this happen in real life, the team needed a special stage, and the material they chose to build it with is one of the stranger substances in modern physics. The Technion Israel Institute of Technology sits in Haifa, on a hill overlooking the Mediterranean. It is one of the oldest and most respected science and engineering universities in the world, and in the early 2020s, a research group there led by Professor Ido Kamener was quietly building something that had never existed before. Not a particle accelerator, not a telescope, an electron microscope so fast and so precise that it could photograph events unfolding in quadrillionths of a second. The instrument combined two cutting-edge capabilities. The first was ultra-fast laser timing, using laser pulses to trigger events and then image them at precisely controlled delays, each delay a tiny fraction of a trillionth of a second apart. The second was a new imaging technique the team was developing called electron interferometry, which used the wave nature of electrons themselves to achieve resolution far below what standard optical microscopes can reach. Together, these two systems allowed the team to capture a kind of slow-motion video of processes that unfold faster than anything previously filmed. The team also partnered with researchers from across the world, institutions including MIT, Harvard, Stanford, Bar-Ilan University in Israel, ICFO in Spain, and the University of Milano Bicocca in Italy. This was a global collaboration, dozens of scientists contributing to a single experiment, and the experiment worked like this. The team chose a sample material, placed it under the electron microscope, and fired an ultra-fast laser at it. The laser triggered the creation of wave patterns inside the material, patterns riddled with phase singularities. The electron beam then imaged the sample at an extremely precise moment after the laser fired. Then they reset everything and did it again. Same laser pulse, same material, slightly later imaging moment. They captured hundreds of these snapshots, each one a frozen frame from the same repeating event, each frame offset from the last by a tiny slice of time. Stack all those frames together and you get a time-lapse. A high-speed movie of phase singularities forming, moving, accelerating and colliding, all compressed into an image sequence sharp enough to track each vortex's motion. The spatial resolution was so fine it could resolve features far smaller than the wave itself. The temporal resolution reached down to timescales the singularities actually operate on. For the first time in the history of the field, the tools matched the problem, but there was still a challenge. Even with the best instruments ever built, the singularities needed to reach superluminal speeds at velocities the system could actually measure. Watching a dark point hit infinite speed inside a wave moving at 186,000 miles per second would still be like trying to photograph a bullet with a slow-motion camera built for traffic. The team needed a way to slow light down, not slow down their camera, slow down light. And the material they chose to do exactly that is one of the most unusual substances in physics today. Light is fast, shockingly fast. But light is only that fast in a vacuum, in empty space, with nothing in the way. The moment light enters any material, glass, water, crystal, anything at all, it slows down. In water, light travels at roughly 75% of its vacuum speed. In glass, closer to 66%. In diamond, about 41%. The denser and more structurally complex the material, the more light slows. The team at the Tachyon needed something far more extreme. They needed light to slow down so dramatically that its local speed inside the material dropped to a tiny fraction of what it does in open space. Only then would the superluminal singularities be moving fast enough relative to the local light speed to be captured by their instruments. The material they chose was hexagonal boron nitride. It does not have a dramatic name. It does not look special. To the naked eye, it is a pale, flat flake thinner than a human hair. Chemically, it is related to graphite, the material in pencil leads, but at the nanoscale, it has a crystal structure so precise and so ordered that it does something extraordinary to light. Inside hexagonal boron nitride, light does not travel freely. Instead, it couples with the atomic vibrations inside the crystal lattice, forming what physicists call phonon polaritons. These hybrid particles are simultaneously light and a mechanical vibration. They are bound to the crystal structure and can only move through it in ways the lattice allows. The result is that light inside hexagonal boron nitride moves at roughly 1% of its normal speed. 1%. Light that normally crosses a football field in about 1 nanosecond now takes 100 times longer to cover the same distance. This seems like it would make superluminal observation harder. If light slows down, the singularities would need even faster absolute speeds to exceed it, right? The opposite is true. And this is the elegant twist at the heart of the experiment. The singularities do not need to exceed light in a vacuum. They need to exceed light locally, inside the material. The relevant speed limit for this experiment is the local light speed in hexagonal boron nitride, which is just 1% of the vacuum value. That makes the singularity's superluminal behavior much easier to reach and much easier to measure. The team was effectively studying a phenomenon that requires extraordinary speed, but in a medium where extraordinary speed starts at a far lower bar. And because the singularity's acceleration toward each other is driven by the wave geometry, not the medium's light speed, they still accelerate to velocities that far exceed even the reduced local limit. 1% of the normal speed of light is still roughly 1,860 miles per second, fast enough to cross the United States in a fraction of a second. And the singularities blew past it. They accelerated. They closed in on each other, and in a burst of motion lasting just 3 quadrillionths of a second, they hit velocities the equations described as formally infinite. But what exactly are phonon polaritons? And why does combining light with sound inside a crystal produce something behaving unlike anything in normal wave physics? Light is pure electromagnetic energy. It has no mass, does not need a medium to travel, and moves through empty space with nothing to interact with. Sound is the opposite. It is mechanical. It needs something to push against. Atoms vibrating, passing energy from one to the next. No medium, no sound. So what happens when you force them together? Inside certain crystals, light does exactly that. When a photon enters hexagonal boron nitride, it does not simply pass through. The electric field of the photon starts interacting with the charged atoms of the crystal lattice. The crystal's atoms are always vibrating at specific frequencies, called phonon modes. When the photon's frequency matches a phonon mode closely enough, the two become entangled. The photon cannot move freely without dragging the crystal vibration with it. The crystal vibration cannot oscillate without carrying the photon along. They merge into a single entity called a phonon polariton, a quasi-particle that is part light and part sound, bound together inside the crystal structure. This is not a metaphor. The physics community uses the term quasi-particle because these are real, measurable objects with defined properties, including a mass, a velocity, and a specific way of interacting with other phonon polaritons. Phonon polaritons move slowly because they are constantly being absorbed and re-emitted by the crystal lattice as they travel. Every interaction takes time. That is what drags their speed down to 1% of the vacuum light speed. But they also do something that free light cannot. They create interference patterns with extraordinary spatial sharpness. Because their wavelength inside the crystal is compressed compared to light and air, the wave features they produce are also compressed, meaning the phase singularities and vortices embedded in those wave patterns are tightly packed and geometrically crisp. This is exactly what the Tachyon team needed. Tight, well-defined singularities that their electron microscope could resolve, moving at speeds their timing system could track. The phonon polaritons formed the stage, the singularities were the actors, and the electron microscope was the camera. What the camera captured took 3/4 of a second to unfold. But the images it produced revealed something that physicists have only been able to imagine since the 1970s. Two dark vortices, spinning in opposite directions, drifting toward each other through the crystal, accelerating faster, then faster still, their velocity climbing beyond any local speed limit. And then the numbers stopped making physical sense. The equation said the velocity at the final moment reached infinity, and then both singularities ceased to exist, simultaneously, gone, not slowed down, not deflected, not absorbed, annihilated by each other. The opposite spins cancelled, the dark points vanished, and the wave pattern closed over the gap as if nothing had happened. In 3/4 of a second, a dark point moved at infinite speed and then disappeared. And the team recorded it on camera. Now, the obvious question: if something hit infinite speed, even for an instant, how can Einstein's rule still be intact? 3/4 of a second. Write that out. 0.003 trillionths of a second. A timescale so short that in that same interval, a beam of light travelling at full vacuum speed covers less than a millimetre, less than the width of a pencil tip. Inside that window of time, the Tachyon team watched two dark vortices do something no instrument had ever captured before. The singularities had formed when the ultra-fast laser pulse hit the hexagonal boron nitride sample. The interference pattern it generated was riddled with phase singularities, each one a point of zero amplitude surrounded by a spinning vortex of wave energy. Pairs of singularities that spun in opposite directions were drawn toward each other by the wave geometry, the way two whirlpools in a river slowly drift together. At first their movement was measurable, finite, fast but trackable. Then something changed. As the distance between them shrank, the acceleration increased. In the language of physics, the singularities' velocity scaled as an inverse function of their separation. The closer together, the faster. The faster, the closer. A runaway feedback loop written entirely in geometry. The team watched the velocity climb past the local speed limit inside the crystal, past twice the local limit, past 10 times. The numbers kept rising with each successive frame of the image sequence, and in the final frames, right before the moment of annihilation, the velocities the team measured formally exceeded any finite value. The math described it as approaching infinity. Two dark points moving at infinite speed, closing a distance of effectively zero in zero time. Then both singularities vanished, simultaneously. The opposite spinning vortices cancelled each other perfectly, and the wave pattern snapped back to normal as if the singularities had never been there. The whole event, from the beginning of measurable acceleration to mutual annihilation, lasted 3/4 of a second. The electron microscope, running its stacking process of hundreds of individually timed snapshots, had caught it. Frame by frame, the time-lapse showed the dark points clearly, their positions shifting across the crystal, their speed visible from the changing gap between frames. This was the confirmation of a 50-year-old theoretical prediction. Optical phase singularities can move at formally superluminal speeds. The experiment documented it directly at spatial and temporal resolutions an order of magnitude beyond any prior state-of-the-art system. Professor Kamener's team published their results in the journal Nature on March 25, 2026, under the title Superluminal Correlations in Ensembles of Optical Phase Singularities. The paper included the full data, the imaging methodology, and the explicit confirmation that what they had observed was consistent with the theoretical predictions from the 1970s. The phenomenon was real, reproducible, and measurable, and none of it violated Einstein. That last point is where most people get confused. If something reached infinite speed in a laboratory, and that is now a documented scientific fact, how does the cosmic speed limit survive intact? The answer comes down to one simple question. What was actually moving? The singularity hit infinite speed. That sentence is true. That sentence is in a Nature paper. And Einstein's rules are completely fine. How? Start here. Einstein's rule protects three things: mass, energy, information. Those three things cannot travel faster than 186,000 miles per second. Any phenomenon that involves none of those three things is exempt. A phase singularity is a mathematical location. It is the point inside a wave pattern where the amplitude equals exactly zero and the phase is undefined. It has no mass, because mass is a property of particles and the singularity is a geometric feature of a field. It carries no energy, because energy in a wave is proportional to amplitude, and the amplitude at singularity is zero by definition. And it cannot encode or transmit information, because it is not an object that can be controlled or modulated to carry a message. What moved in the tachyon experiment was not a thing, it was the shifting position of a mathematical feature. Here is the best comparison. Imagine scissors. Hold them open, with the blades spread wide, and then close them slowly. The point where the two blades intersect moves along the length of the blades as they close. If the blades are long enough, and you close them fast enough, that intersection point can technically move faster than the blade edges themselves. If the blades were thousands of miles long and you slammed them shut, the intersection could cross that distance faster than light. Has any part of the physical scissors moved faster than light? No. The blades move slowly. Only the intersection, the geometric meeting point of two physical objects, sweeps fast, and the intersection cannot be used to send a letter, carry energy, or transmit a signal. The dark vortices in the experiment work the same way. The phonon plaritons carrying the wave pattern were not themselves moving faster than the local light speed. The wave was obeying all normal physics. Inside the wave, the location called the singularity was shifting rapidly, driven by the wave geometry, not by any physical transport. The team at the Technion made this distinction explicit in their paper. They described the singularities as analogous to a river vortex that moves faster than the water flowing around it. The water, the actual physical substance, obeys the river's rules. The vortex, the geometric pattern in the water, can shift faster than the flow itself. No mass moved superluminally. No energy was transmitted superluminally. No information jumped from one place to another at superluminal speed. The causal structure of the universe, the rule that effects cannot precede their causes, remained fully intact. Einstein's framework handles this precisely. Physicists distinguish between phase velocity, group velocity, and signal velocity in any wave system. Signal velocity, the speed at which actual information travels, cannot exceed light. The dark vortices displayed superluminal behavior in the geometric sense, moving as patterns in a wave, while the signal velocity of the underlying wave stayed well within bounds. But here is the part that genuinely stretches the brain. If the singularity is just a mathematical feature with no physical substance, what does it mean to say it moved at all? And how do we talk about velocity for something that, technically, has no existence between measurements? That question leads somewhere surprisingly deep, and the answer involves a concept most people have never heard of. Here is a thought experiment. You're standing in a field at night. You have a laser pointer. Directly above you, 240,000 miles up, is the surface of the moon. You point the laser at the moon's surface, and you see a small red dot appear. Now you swing your wrist. Slowly at first, then faster. The dot moves across the moon's surface. Question: how fast can that dot move? The answer is, as fast as you want. With a fast enough wrist movement, the laser dot can sweep across the full width of the moon, roughly 2,000 miles in far less than a millisecond. The crossing speed of the dot can easily exceed the speed of light, and no physics is violated, no equation breaks. Einstein remains unbothered. Why? Because the dot is not a thing. It is not travelling from one side of the moon to the other. It is the intersection of a beam of light and a surface. The beam itself is travelling straight from your hand to the moon at 186,000 miles per second. The dot you see is wherever the beam currently lands. When you swing your wrist, you're not sending an object from point A to point B. You're changing which photons are hitting which part of the moon. Each photon makes a straight line trip at full light speed, but the relationship between where you point and where the beam hits can shift as fast as your wrist allows. No information travels across the moon's surface during this process. Someone standing on the moon at point A cannot use the moving dot to send a signal to someone at point B. The dot appears where the beam lands, not because anything travelled from A to B at the dot's speed. The causal chain stays inside the beam, which never breaks any rules. The phase singularities in the tachyon experiment work by exactly the same principle. They are the intersection point of multiple overlapping waves. They have no internal structure. They cannot carry a payload. They appear at a location defined by wave geometry, and as the wave geometry evolves, that location shifts. The difference between the laser dot and the singularities is that the singularities are embedded inside a medium, following dynamics described by more complex wave equations. But the core idea is identical. A geometric feature of a wave pattern can shift faster than the wave itself without any physical object making that journey. This principle shows up in physics in several places, and physicists have a formal vocabulary for it. When dealing with waves, there are actually three distinct kinds of velocity that can describe how fast something moves. Phase velocity describes how fast the peaks and troughs of the wave move. This can exceed light speed in many common situations, such as inside a waveguide or in certain resonant systems. Group velocity describes how fast the overall envelope of a wave packet moves. Under certain conditions, this can also exceed light. And signal velocity describes how fast an actual informational discontinuity, a real message, propagates. This one cannot exceed light. Ever. The other two can do almost whatever they want. The singularities in the experiment were displaying superluminal motion at the phase and geometric level. The signal velocity of the underlying wave was never a problem. Now, the laser dot example is intuitive, but it is also simple. The tachyon result is far more precise and technically rigorous. And to really understand why the experiment produced what it did, you need to understand the tool they used to see it. Waves are sneaky. Most people think of a wave as one thing moving in one direction at one speed, like a sound wave from a speaker, or a ripple spreading across a pond. One wave, one speed. But real waves, especially in physics, carry multiple layers of motion inside them, and each layer can move at a completely different speed. This is one of the most counterintuitive ideas in wave physics, and it is central to understanding what the tachyon experiment actually measured. Start with phase velocity. Imagine a wave moving toward you. The wave has peaks and troughs. Now focus on one peak, just one. Track where that peak is from one moment to the next. The speed at which that specific peak moves forward is the phase velocity. phase velocity can be surprisingly fast. In certain materials and wave configurations, the peaks of a wave can slide forward faster than light. This does not mean anything physical travelled faster than light. The peak is not an object. It is a feature of the wave's pattern, and the movement of a pattern feature does not carry information from one place to another. Next, group velocity. Most waves in the real world are not a single pure tone. They are actually a combination of many waves at slightly different frequencies, all overlapping. This combination creates a shape, an envelope, a packet with a beginning and an end. Think of a drum beat. It has a clear start, a peak of loudness, and then it fades. The overall shape of that packet moves at the group velocity. Group velocity is more physically meaningful than phase velocity. It roughly corresponds to the speed at which the wave packet as a whole travels. For most everyday waves, group velocity is slower than phase velocity and stays below the vacuum light speed. But under special conditions, including in certain resonant optical systems, group velocity can also exceed light, or even become negative, meaning the peak of the wave appears at the end of the pulse before it appears at the beginning, a truly bizarre effect. Both of these velocities, phase and group, can exceed light in vacuum without violating any known physics. They are properties of wave geometry, not vehicles for information. Signal velocity is different. Signal velocity describes the speed at which a real, informational discontinuity travels. Imagine a wave that has been perfectly flat for a long time and then suddenly changes. A clear, sharp edge that represents a piece of information, an on or an off, a yes or a no. The speed at which that sharp edge propagates is the signal velocity. Signal velocity cannot exceed the vacuum speed of light. This is what Einstein's rule actually protects. No sharp edge carrying real information can outrun light. The math of wave propagation, combined with the special theory of relativity, makes this exact and absolute. So the three velocities give us a clean picture. Phase velocity and group velocity are wave geometry properties, flexible and sometimes superluminal. Signal velocity is the information carrier, fixed and bounded by light. The phase singularities in the Tachyon experiment were moving as geometric features of the wave pattern. Their motion was a phase-level phenomenon. The team measured phase-level superluminal behaviour precisely because that is what the theoretical prediction from the 1970s described. Signal velocity was never involved. The experiment was not moving information at superluminal speeds. It was watching the geometry of a wave unfold at speeds the geometry allows, which are unlimited. Now, if this is all happening at scales smaller than a hair and faster than a blink, how did the team actually see it? Seeing a phase singularity is hard. Seeing one move at superluminal speed is something else entirely. The spatial scale of the event, inside a crystal flake thinner than a hair, is far below what any optical microscope can resolve. The timescale, 3 quadrillionths of a second from start to annihilation, is far below what any standard camera can capture. For 50 years, the prediction sat unconfirmed for exactly this reason. The tools were not good enough. The Tachyon team built tools that were. The core instrument was an ultra-fast transmission electron microscope. Standard electron microscopes use a beam of electrons to image materials at the nanoscale, achieving resolutions far beyond what light-based systems can reach, because electrons have much shorter wavelengths than visible light. The Tachyon's version was modified to operate in ultra-fast mode, meaning the electron beam could be precisely timed to image the sample at specific moments after an event was triggered. The triggering system used an ultra-fast laser. When the laser fires, it creates the phonon-polariton waves inside the hexagonal boron nitride sample, which generates the interference pattern and the phase singularities. The laser also sends a timing signal to the electron microscope, telling it exactly when to capture an image. By adjusting the delay between the laser pulse and the electron imaging moment, with precision down to sub-femtosecond intervals, the team could choose exactly which slice of time to photograph, fire the laser, wait exactly a certain number of femtoseconds, image the sample, reset, repeat. Each time a slightly longer delay. Hundreds of these individual snapshots, each one a frozen frame from the same repeating event, accumulated into a data set. Stack them in order by delay time, and you have a time lapse. A frame-by-frame movie of the singularities forming, drifting, accelerating, and vanishing. But even with that technique, the spatial resolution had to match the spatial scale of the singularities themselves, features far smaller than the phonon-polariton wavelength. A standard electron microscope would blur them out. The team's solution was electron interferometry. Instead of imaging the sample with a straightforward electron beam, they used the interference between two electron paths to extract phase information directly. This allowed them to resolve features far below the standard resolution limit of the instrument, achieving spatial resolution an order of magnitude beyond what was previously possible for this type of measurement. Combined with a femtosecond timing system, the result was a tool that could see spatial features smaller than the wave and temporal features shorter than the wave cycle, both improved by an order of magnitude compared to prior state-of-the-art systems. Nobody had that before. The Technion team built it specifically for this experiment, and it worked. The time-lapse showed the singularities clearly. Their position shifted across the crystal from frame to frame. By measuring the distance travelled between consecutive frames and dividing by the time between those frames, the team calculated velocities. And as the singularities approached each other, those velocities climbed past the local light speed in the crystal, then kept climbing, until the numbers formally exceeded any finite value. The experiment recorded what no instrument had ever recorded before: darkness moving faster than light, captured in a sequence of frames. What made this possible was not just brilliant science, it was 50 years of waiting for the technology to catch up to the math. And now that it has, the question shifts from, can we see it, to what else does this tell us? The prediction was made in the 1970s. A physicist working through the mathematics of wave interference calculated that optical phase singularities should be able to exceed the speed of light under specific conditions. The math was clean, the logic was sound, the prediction was published, and then it waited. 50 years. That is roughly how long the internet has been a part of daily life. Long enough for an entire generation of physicists to enter the field, build careers, and retire without ever seeing this particular prediction tested. It sat in the literature as a theoretical curiosity, cited occasionally, revisited in review papers, but never directly confirmed. The reason was purely technological, and it was brutally simple. The event happens at scales the instruments of the day could not reach. Spatially, the singularities are features inside a phonon-polariton wave. Those waves have extremely short wavelengths inside the crystal. The singularities themselves are smaller still, features within the wave pattern. Resolving them requires spatial resolution below the wavelength of the wave being studied. Standard optical microscopes cannot go below the diffraction limit, roughly half the wavelength of the light they use. For visible light, that is several hundred nanometers. The features in the Technion experiment were far smaller. Optical microscopes were useless for this task. Electron microscopes can go much smaller. But standard electron microscopy takes time to acquire an image. Scanning across a sample takes milliseconds. The singularity event unfolds in 3 quadrillionths of a second, 12 orders of magnitude faster than a standard electron microscope image acquisition. So even the best available tool for spatial resolution was too slow by a factor of 1 trillion. Ultra-fast lasers started becoming powerful enough for femtosecond work in the 1990s and 2000s. But coupling femtosecond laser timing with electron microscopy, and then developing electron interferometry to push spatial resolution below the wavelength limit, required another decade or more of instrument development. The Technion team's paper explicitly describes their approach as achieving both spatial and temporal resolution, each improved by an order of magnitude beyond prior state-of-the-art systems. an order of magnitude means 10 times better, for both spatial and temporal resolution simultaneously. That combination, 10 times sharper and 10 times faster than the best previous tools, is what finally made the measurement possible. And there is a strange poetry to the timeline. The original prediction was made around the same time that the first programmable calculators were becoming available to researchers. The confirmation came in an era where AI systems can simulate quantum materials and electron microscopes can photograph atomic bonds. The gap represents the full span of the digital revolution beginning to present. For 50 years the universe knew the answer. Physicists knew the question. Only the tools were missing. Now that the tools exist, the implications reach well beyond this one experiment. Because phase singularities appear in every wave system in nature. Sound, water, quantum fields, superconductors. The dynamics documented in the Tachyon experiment are universal. And the technologies that come from understanding those dynamics, things like quantum information encoding, nanoscale materials imaging, and next-generation microscopy, are only now becoming visible on the horizon. Before we get there though, it is worth stopping to realise that the Tachyon result is only the most recent entry in a much longer list. The universe has been hiding faster-than-light phenomena in plain sight for decades. Some of them are visible every day, in places most people walk past without a second thought. Walk up to the edge of an active nuclear reactor pool and look down. The water glows blue, a deep, electric, steady blue. No lights under the surface. The water itself is producing light, and it does it continuously, as long as the reactor runs. This is not a special effect. It is not a design choice. It is a direct consequence of something travelling faster than light. Confirmed. Happening right now in reactors around the world. Here is how it works. Light in a vacuum moves at 186,000 miles per second. But light in water moves slower, about 75% of that vacuum speed, roughly 140,000 miles per second. That reduced speed is still extraordinarily fast, but it is slower. Nuclear reactors produce energetic particles as a byproduct of their reactions. Some of these are electrons carrying enormous amounts of energy. When those electrons enter the reactor's water coolant, they are moving faster than light moves inside the water. Not faster than light in a vacuum, faster than light in the specific medium of water, and when a charged particle travels faster than the local speed of light in its medium, something extraordinary happens. The particle generates a shock wave. Think of a jet breaking the sound barrier. Sound travels at a specific speed through air. When a jet exceeds that speed, the compressed air cannot get out of the way fast enough, and a cone-shaped shock wave forms behind the aircraft. That is the sonic boom. The same geometry applies to light. When the electron outruns light in the water, it produces an electromagnetic shock wave. A cone of light radiates outward behind the moving electron, just like the pressure cone behind a supersonic jet. That cone of light is blue. The specific wavelength is determined by the particle's speed and the optical properties of water, and it is called Cherenkov radiation, named after the Soviet physicist Pavel Cherenkov, who first described it in 1934. Cherenkov radiation is visible proof right now, in operational facilities, that particles can and do exceed the local speed of light in a medium. The electrons are not breaking any cosmic rule. They are moving below the vacuum speed of light, but they are above the local limit inside the water, and the physics responds accordingly. This is one of the most visually striking examples of what physicists call a loophole in the casual understanding of the speed limit. Light in a medium is slower than light in a vacuum, and particles can exceed the medium's limit while respecting the vacuum limit. The same logic, applied to a crystal instead of water, is part of the foundation of the Tachyon experiment. The phonon polaritons in hexagonal boron nitride move at 1% of the vacuum speed of light. The phase singularities move faster than that local limit. Cherenkov radiation is the real-world, everyday version of the same idea, just blue, glowing, and visible to the naked eye. The universe has been showing us faster-than-light loopholes in nuclear reactor pools for decades. Most people just never knew what the glow meant, and the next loophole on the list operates at a scale even stranger than that, because it involves particles that cheat walls. Place a particle in front of a wall. In classical physics, the rule is simple. If the particle does not have enough energy to climb over the wall, it bounces back. The wall holds. End of story. Quantum mechanics disagrees. At the scale of electrons, protons, and other subatomic particles, walls are not solid barriers. They are regions of higher energy, and quantum mechanics says that a particle does not have a single, definite position or energy at any given moment. Instead, it exists as a spread-out probability, a wave function that extends in all directions, including through the wall itself. Even if the particle does not have enough energy to classically cross the barrier, its wave function has a small but non-zero probability of existing on the other side. And sometimes, with a probability that physics can calculate precisely, the particle simply appears on the other side. This is quantum tunneling. The particle does not climb the wall. It does not break the wall. It tunnels through the energy barrier as if the wall were not quite solid. This is not theoretical. It is the mechanism that powers the nuclear fusion inside stars. Hydrogen nuclei inside a stellar core do not have enough energy to overcome their mutual repulsion and fuse. Classically, fusion should not happen. Quantumly, the nuclei tunnel through the repulsive barrier and fusion occurs. Without tunneling, stars would not shine. Tunneling also powers modern electronics. Tunnel diodes, flash memory chips, and scanning tunneling microscopes all rely on quantum tunneling as a core operating principle. It is a foundational process in our technology. Now here is where it gets strange. When a particle tunnels through a barrier, how long does the crossing take? Classical intuition says it should depend on how thick the barrier is. Thicker wall, longer crossing time, lower effective speed. Simple. Experiments say otherwise. And the name for what experiments actually find is one of the more quietly disturbing results in all of physics. In 1962, a physicist named Thomas Hartmann was working through the mathematics of quantum tunneling. He made a calculation. He found that when you increase the thickness of a quantum barrier, the tunneling time does not increase proportionally. In fact, past a certain barrier thickness, the tunneling time essentially stops increasing at all. Make the barrier twice as thick. The time stays nearly the same. Make it 10 times as thick. Still nearly the same. This is called the Hartmann effect. What does this mean for speed? If the particle crosses a thicker barrier in the same time as a thin one, then its effective velocity through the barrier grows as the barrier thickens. For very thick barriers, the implied velocity exceeds the speed of light. For extremely thick barriers, the implied velocity becomes arbitrarily large, approaching infinity. This is experimentally confirmed. The effect has been measured in multiple laboratories using microwave signals, laser pulses, and electron systems. The results are consistent. Tunneling time does plateau, and the implied effective velocity does exceed light for thick enough barriers. And yet, no physicist believes information is actually being transmitted faster than light. Here is why. The confusion arises from treating tunneling as if the particle is physically travelling through the barrier. A particle on one side, a barrier in the middle, a particle appearing on the other side. If you model that as a journey, the speed calculation gives superluminal numbers. But tunneling is not a journey through space. The wave function of the particle exists on both sides of the barrier simultaneously. The particle does not start on one side and physically traverse the barrier to reach the other. The process is fundamentally non-spatial in a way that classical thinking cannot capture. Physicists describe it as quantum non-locality. The particle's wave function is spread across the barrier, and what we call tunneling is the collapse of that spread out probability to a definite location on the far side. There is no trajectory. There is no path taken. And because there is no path, calculating a speed from distance divided by time gives a number that reflects the geometry of quantum mechanics, not a physical velocity. No signal, no message, and no information crosses the barrier faster than light. The Hartmann effect is real. The superluminal implied velocity is real. But it is a property of quantum non-spatiality, not of physical transport. The universe keeps playing the same trick. Something appears to break the rule. And then careful analysis shows the rule was never in reach to begin with. Tunneling is arguably stranger than the dark vortices, because at least the vortices are a geometric feature of a visible wave. Tunneling involves particles that exist in multiple places simultaneously, and then choose, probabilistically, which place they actually are. And there are more surprises ahead. Because the universe is not just hiding loopholes inside crystals and particles, it hid one inside the expansion of space itself, and that one has been running since the beginning of time. A particle on one side of a wall, a particle appearing on the other side. Time passes. It looks like a crossing. But quantum mechanics says that framing is wrong from the start. The reason the Hartmann effect does not violate Einstein is the same reason the laser dot on the moon does not violate Einstein. The thing that appears to move does not exist as a physical object between the two locations. There is no path. There is no trajectory. There is no particle travelling through space at superluminal speed. To understand why, start with what the wave function actually is. Every quantum particle, an electron, a proton, a neutron, has a wave function. This is a mathematical description of all the possible states the particle could be in and the probability of each. The wave function is spread out through space. Everywhere the wave function has non-zero value, the particle has some probability of being found there. When a particle faces a potential barrier, an energy wall it classically cannot cross, the wave function does not stop at the barrier edge. It extends through it, exponentially decaying in amplitude but never reaching exactly zero. This tail of the wave function that extends through and beyond the barrier is what makes tunneling possible. The particle does not decide to cross. The particle does not move through the barrier. What happens is that the wave function, already partly present on the far side of the barrier, collapses into a definite location there. The particle is found on the far side. There is no moment at which the particle was inside the barrier. There is no moment at which it was halfway through. It was on one side, described by a spread-out probability, and then it was on the other side. The word crossing is a narrative shortcut, not a description of what actually happened. This is quantum non-spatiality. Space as a concept does not fully apply to quantum processes the way it applies to a car driving down a road. And this is why the Hartmann effect, despite showing apparent superluminal speeds for thick barriers, does not allow faster-than-light communication. There is no spatial path for information to ride. The particle's appearance on the far side of the barrier does not transmit a message from this side to that side. It reflects the collapse of a probability distribution. No cause and effect chain travels through the barrier faster than light. Physicists from the University of Warsaw and Oxford published work in 2024 revisiting the theoretical foundations of this argument, confirming that quantum tunneling is compatible with relativity precisely because of its non-spatial nature. The system is weird, but it is consistent. What all of these examples, the dark vortices, the laser dot, Cherenkov radiation and quantum tunneling, have in common is a single underlying structure, something that appears to move or even exceed light speed, but carries nothing that Einstein's rule protects. No mass in transit, no energy transported, no information encoded and delivered. The cosmic speed limit has never once been broken. It has only been misread. There is one more place where the universe routinely exceeds the speed of light, and it is the largest and oldest example of all. It has been happening since the universe began, and you cannot stop it, reverse it, or ever overcome it with any technology humanity could ever build. The universe is getting bigger. Not in the way a balloon gets bigger when you blow air into it, with the rubber stretching and the air pushing outward from a centre. The universe has no centre. It has no edge in the way a balloon does. Space itself is expanding, and it is expanding everywhere simultaneously, in every direction, at every point. Every galaxy is moving away from every other galaxy, not because they are flying through space, because the space between them is growing. Picture dots drawn on the surface of a balloon. As the balloon inflates, the dots move apart. The dots are not crawling across the rubber. The rubber itself is stretching, and the dots go with it. Now measure how fast distant galaxies are receding. Nearby galaxies, a few tens of millions of light years away, are receding slowly. The expansion adds up over distance. The farther a galaxy is, the faster it appears to move away from us. Astronomers discovered this relationship in the early 20th century and called it the Hubble expansion. Here is where it gets strange. Past a certain distance, roughly 14 billion light-years away, galaxies are receding from us faster than the speed of light. The galaxies themselves are not moving through space at superluminal speed. Space is simply expanding fast enough between them and us that the distance grows at a rate exceeding 186,000 miles per second. This is confirmed observational cosmology, the edge of the observable universe, the boundary of the region from which light has had time to reach us since the beginning of the universe, is receding from us at roughly 3 times the speed of light right now. And it has been doing so for most of the universe's history. Einstein's rules are fine. General relativity, Einstein's theory of gravity and space-time, places the speed limit locally. It says that within any small region of space, nothing carrying mass, energy, or information can exceed light speed relative to its immediate surroundings. The expansion of space itself is not a local motion. It is a global geometric change, operating under different rules. Think of it this way. 2 ants on opposite ends of a rubber band cannot crawl toward each other faster than their top crawling speed. But if someone stretches the rubber band fast enough, the distance between the ants grows regardless of how fast they crawl. The ants are obeying all the ant speed rules. The rubber band is doing something the rules never addressed. Galaxies beyond the boundary of our observable universe are not just far away, they are unreachable. Even light travelling at full vacuum speed from those galaxies in our direction is losing ground to the expansion. The distance between those galaxies and us grows faster than light can close it. They will never reach us, and we will never reach them. That boundary is not a physical wall. It is a consequence of geometry and expansion rate, and it has been quietly sealing off portions of the universe from us for longer than Earth has existed. But losing access to distant galaxies is one thing. Understanding what that means for the future of everything is something far more unsettling. Every second, the observable universe loses ground. Galaxies that are currently at the edge of what we can see are drifting toward permanent invisibility. The light they emit right now is travelling toward us at full speed, but the space between us and them is expanding fast enough that the light emitted from beyond a certain boundary will never close the gap. It will travel toward us forever, gaining no ground, and eventually fade into a longer and longer wavelength as the expansion stretches it. This boundary is called the cosmological event horizon. It is the spatial equivalent of the event horizon around a black hole, a point of no return, except that instead of surrounding a collapsed star, it surrounds us. We are inside it. Everything beyond it is permanently beyond reach. The Milky Way and the few dozen galaxies gravitationally bound to it in what astronomers call the local group will eventually be all that remains gravitationally accessible. Every other galaxy, every other cluster, every other structure in the cosmos will be moving away faster than any signal or ship could follow. Cosmologists calculate that in roughly 150 billion years, the observable universe will have grown so empty of reachable content that a civilization living then would look out and see only the merged remnant of the local group's galaxies, surrounded by a void. The evidence that a larger universe exists at all, the cosmic microwave background, the redshifted light of distant galaxies, the large-scale structure of the cosmos, will have been redshifted to undetectability. A future civilization with no record of 21st century astronomy would have no way to know the universe contained anything beyond their galaxy cluster. That is what the expansion rate means at its logical end: permanent informational isolation, an increasingly empty observable region, a universe that forgets its own scale. We are living in a privileged moment. Right now, in the 21st century, we can still see the evidence. We can still map the cosmic structure, measure the expansion, trace the origins. The evidence is still arriving. It will not always be arriving. This is the largest and oldest example of faster-than-light recession in the known universe. It has been ongoing since roughly the first seconds after the Big Bang. It governs the ultimate boundary of what any civilization on Earth or anywhere else can ever know or reach. And yet, a handful of theoretical physicists have spent the last 3 decades asking whether there is a way around it, whether a sufficiently advanced civilization could engineer a loophole in the expansion rate itself, whether space could be bent, compressed, or warped in a way that moves a ship faster than light without ever making the ship itself move faster than light. In 1994, one physicist wrote down an equation that suggested the answer might be yes. Miguel Alcubierre was 30 years old, a Mexican physicist finishing his doctoral work at the University of Wales, when he sat down and designed a faster-than-light engine. He published it in 1994 in a journal called Classical and Quantum Gravity. The paper was titled The Warp Drive, Hyperfast Travel Within General Relativity, and it described in rigorous mathematical terms a mechanism for travelling between stars faster than light without violating a single equation. The key insight was this: general relativity places the speed limit locally. Within any small patch of space, nothing carrying mass or information can exceed light. But general relativity also allows space itself to curve, stretch, and compress. The expansion of the universe is one example. Black holes are another. And Alcubierre asked a simple question: what if you engineer the curvature? His solution creates what physicists call a warp bubble. Imagine space in front of the ship being compressed, shortened, the distance between the ship and its destination made smaller, and simultaneously, space behind the ship is expanded, stretched out, the distance from origin to ship made larger. The ship sits inside a bubble of flat, normal space-time, experiencing no acceleration, no relativistic time dilation, no exotic physics at all. Comfortable, normal, zero gravity conditions. The bubble itself moves through space, carrying the ship with it. Locally, the ship is stationary. The space-time geometry around it is moving. The ship does not travel through space faster than light. Space carries it faster than light. From outside the bubble, an observer would see the ship arrive at its destination in less time than light could have made the trip. From inside the bubble, the crew would experience normal physics throughout the journey. Alcubierre's math described this precisely. The equations satisfied general relativity at every point. No singularity, no violation of local physics, no paradox. The ship's proper velocity through its own local space-time never exceeded light. The physics community found the paper fascinating and deeply problematic simultaneously. Fascinating because the geometry was valid, problematic because of what it required. To create that specific curvature pattern, the math demanded a region of space-time with negative energy density, energy that is less than zero, more negative than a vacuum. That kind of matter is called exotic matter. It is not known to exist in the quantities required. Some quantum effects produce tiny regions of slightly negative energy density, the Casimir effect between metal plates being the most famous example. But the amounts involved are microscopic. Alcubierre's original calculation required exotic matter in quantities that dwarfed entire planets. And there was a second problem. If the bubble was moving faster than light, the people inside could never send a signal forward to control what the bubble was doing. They would be causally disconnected from the front of the bubble. Steering a warp drive faster than light would be like trying to steer a car from inside the trunk with no controls. So the physics community filed the Alcubierre drive under mathematically interesting, physically impossible, an elegant piece of theoretical work that demonstrated a loophole in the letter of relativity while being blocked by the practical requirements of nature. And there it sat for 30 years, until someone started working on removing the problems one by one. Alcubierre's original 1994 proposal required an amount of exotic matter with negative energy roughly equal to the mass energy of the planet Jupiter. Jupiter has a mass of about 1,300 Earths. Its mass energy, using Einstein's mass energy equation, is a number almost beyond comprehension, and the original warp drive needed that much negative energy, which does not exist in usable form anywhere in the known universe. To get a sense of scale, the total energy output of our star over its entire 10 billion year lifetime is a fraction of what the original Alcubierre drive required. Every nuclear weapon ever built, detonated simultaneously, would contribute an almost unmeasurably small percentage of that energy budget, and all of it would need to be negative, less than nothing. Physicists spent the years after the paper's publication trying to reduce those requirements. In 1999, a physicist named Chris van den Broek modified the geometry of the bubble. Instead of maintaining a large internal volume at full size, he proposed a design where the bubble exterior was extremely small, a sphere just larger than an atomic nucleus in radius, but the interior was expanded to a habitable volume through a second layer of warping. This geometric trick reduced the exotic matter requirement from Jupiter mass to roughly 1 gram of negative energy. 1 gram! Still exotic matter that does not exist in usable quantities, but a reduction by a factor of around 10 to the 28th power compared to the original proposal. A 30-year improvement in theoretical efficiency achieved by changing the shape of the bubble. Other researchers contributed further reductions through the 2010s. A physicist named Harold White at NASA's Johnson Space Center proposed that making the bubble ring-shaped instead of spherical and oscillating its intensity over time could reduce the exotic matter requirement further. None of these modifications solve the fundamental problem. Exotic matter with negative energy density remains a requirement, and while quantum physics allows tiny pockets of negative energy to exist, producing them in any macroscopic quantity remains entirely beyond known physics. The energy problem is what kept the Alcubierre drive in the category of theoretical curiosity for 3 decades. Then in 2024, a team of researchers published a paper that changed the conversation entirely, and what made it different from everything that came before was a single, radical decision. They removed the exotic matter entirely. In May of 2024, a team led by Jared Fuchs at Applied Physics and the University of Alabama in Huntsville published a paper in Classical and Quantum Gravity with a title that reads almost like a provocation: Constant Velocity Physical Warp Drive Solution. The word physical was doing enormous work in that title. Every prior warp drive proposal required something physically unreal, exotic matter with negative energy density. Fuchs and his team set themselves a different constraint. They decided to build a warp drive solution using only matter and energy that actually exist, that obey all known physical laws, that satisfy every energy condition in general relativity. No exotic matter, no negative energy, no physics that does not exist, and they found a solution. The solution is a shell of ordinary matter surrounding a passenger volume. The matter is arranged in a specific geometric configuration, and energy flows through the system in a controlled pattern. The space-time curvature this produces creates a warp effect inside the shell, reducing the effective distance the passenger volume needs to travel. This is genuinely new. Every warp drive concept before this one required something that does not exist. The Fuchs model requires only things that do exist, specifically large amounts of ordinary energy configured in a precise way. Miguel Alcubierre himself, the physicist who invented the original concept in 1994, reviewed the paper and endorsed it. The inventor of the warp drive concept confirmed that his successors had found a physically realizable version. The paper was peer-reviewed and published. The physics community accepted it as a legitimate advance in theoretical propulsion research. So is this a warp drive? Can we build it? Not yet. And there is one major catch that keeps it in the theoretical column for now, though a smaller catch than it used to be. Fuchs described the mechanism of his team's warp drive in terms that make the physics surprisingly clear. He said, "Warp relies on large amounts of energy moving rapidly around the passenger volume, which creates a conveyor belt effect on the inside. Picture a conveyor belt at an airport. The walkway moves forward at a steady speed. You stand on it and walk. Your speed relative to the ground is your walking speed plus the conveyor belt speed. Now imagine a conveyor belt that wraps all the way around you in 3 dimensions, flowing forward in front, backward behind, sideways on the sides. Space itself becoming the moving walkway. That is the conceptual model. The rapid circulation of energy around the passenger bubble produces a curvature effect in the space-time immediately surrounding it. Space-time ahead of the bubble is subtly compressed. Behind it, subtly expanded. The passenger inside experiences flat, normal physics. From outside, the bubble as a whole moves through space more efficiently than it otherwise could. The mechanism requires massive amounts of energy, not exotic energy, regular energy, the kind that obeys the same physics as everything else in the universe. But regular energy in amounts that are, as Fuchs described them, still enormous at present. Enormous enough that building the required energy configuration is far beyond anything humanity has engineered or could engineer with any currently visible technology. The geometry of the system is specific. The shell of matter must be arranged so that the energy circulation produces the right curvature pattern. Too much energy in one direction, too little in another, and the warp effect collapses. The precision requirements are extraordinary. But the physics itself is sound. That is the key advance. No new particles, no speculative materials, no energy conditions that nature forbids. The Fuchs model lives entirely within the known laws of general relativity, and Alcubierre's endorsement carried weight. He spent 3 decades watching proposals fail because they required impossible ingredients. When he reviewed Fuchs's work and confirmed its physical validity, it meant the 30-year-old problem of the exotic matter requirement had been genuinely solved. The remaining problem, the one that still keeps this out of the engineering column, is speed. The Fuchs model is physically real. The Fuchs model does not go faster than light. The model operates at subluminal speeds, meaning below the vacuum speed of light. The warp effect reduces the effective distance of travel, making the journey more efficient, but the bubble itself does not exceed the cosmic speed limit. This is not a minor limitation. The entire appeal of warp drives in popular imagination is faster than light travel, reaching other stars in years instead of centuries, crossing the galaxy in a human lifetime. The Fuchs model, as published, does not achieve that. Why? The mathematical challenge is this. Pushing a warp bubble from subluminal speeds to superluminal speeds involves crossing a threshold, the point at which the bubble velocity equals the vacuum speed of light. What happens to the physics at that transition point, and whether the bubble can pass through it without reintroducing exotic matter requirements or violating other energy conditions, remains an unsolved problem. Fuchs and his team acknowledged this explicitly. They describe pushing through to superluminal speeds as an open question. The paper did not claim to have solved it. It claimed to have solved the physically realizable version of the subluminal case, which is a real and meaningful advance, but a partial one. Think of it as proving that a boat can sail. The question of whether that same boat can fly remains unanswered. There are also additional theoretical concerns. General relativity in the extreme regimes near light speed involves effects that are computationally and mathematically difficult to resolve. The curvature patterns that work cleanly at subluminal velocities may change in ways that require new solutions at superluminal velocities. Researchers have not yet worked out what those solutions would look like, or whether they exist within the energy conditions the Fuchs model obeys. The honest summary is this: in 2024, physicists proved for the first time that warp drive effects are physically achievable using real matter and energy. That is a genuine breakthrough. The next question, whether those effects can be extended through and beyond the speed of light, remains open. And yet, the Tachyon dark vortex experiment proved that the universe genuinely allows phenomena that exceed the local speed of light without violating any law. The warp drive research proved that space-time can be curved with real matter to produce real propulsion effects. Two separate research fronts, both advancing simultaneously toward a destination nobody has reached yet. Meanwhile, the foundational rule itself, Einstein's speed limit, was being tested at the same time with more precision than ever before in history, and the results of that test were unambiguous. In November of 2025, a team of researchers in Spain published what became one of the most precise tests of special relativity ever conducted. The team, working out of the Universitat Autónoma de Barcelona and the Institute for Space Studies of Catalonia, was not looking to confirm Einstein. They were, as researchers usually are, looking for cracks, for any measurable deviation from the predictions of special relativity, any sign that the framework might break down at extreme energies or large scales. They found none. Their method used gamma rays, the highest energy form of light, streaming from powerful astrophysical events across billions of light-years of space. Gamma rays from sources like gamma-ray bursts and active galactic nuclei travel enormous distances before reaching Earth. If special relativity were not perfectly accurate, if the speed of light varied even slightly with energy or direction, those variations would accumulate over billions of light-years and become detectable. The team developed a new statistical method that let them combine data from multiple astrophysical sources simultaneously, extracting far more statistical power than any single source analysis could achieve. The result was a test of what physicists call Lorentz invariance, the principle that the laws of physics are the same regardless of how fast you are moving. The new bounds they set on any possible violation of Lorentz invariance were 10 times tighter than any previous measurement, an order of magnitude more precise than the prior state of the art, and the answer was no violation found. Einstein's framework, including the invariance of the speed of light, held to 10 times greater precision than it had ever been tested before. The researchers noted almost with humour that they had hoped to find something wrong. Like every generation of physicists before them, they wanted to be the ones who caught a crack in relativity. Like every generation before them, they did not. This matters in the context of everything else happening in this story. The dark vortex experiment confirmed something moves faster than light. The warp drive research confirmed space-time can be curved with real matter. And simultaneously, the most precise test of Einstein's framework in history confirmed the framework itself is more accurate than ever. All three findings are consistent. None of them contradict each other. The apparent loopholes work precisely because of how the rule is written, and the rule, checked 10 times greater precision, is solid. The universe is operating exactly as Einstein described, and the strangest implication of that is what the speed limit is actually protecting. Every law of physics contains an assumption so fundamental that it is rarely stated out loud. The assumption is this: physics works the same way everywhere, in every direction, for every observer moving at any constant velocity. A physicist in a lab in Tokyo and a physicist in a lab in Sao Paulo, both running the same experiment, get the same results. A physicist moving at 90% of the speed of light runs the same experiment and gets the same results. The laws do not change based on location, orientation, or velocity. This principle is called Lorentz invariance. It is named after the Dutch physicist Hendrik Lorentz, who, along with Einstein, helped establish its mathematical form in the early 20th century. Lorentz invariance is not just a nice idea. It is structurally baked into the equations of special relativity, quantum mechanics, and quantum field theory. Essentially, every successful theory in modern physics assumes it at a foundational level. If Lorentz invariance were violated, even slightly, the entire architecture of modern physics would require rebuilding from the ground up. And the speed of light being constant for all observers is one of the most direct consequences of Lorentz invariance. If the speed of light varied depending on direction or the observer's velocity, Lorentz invariance would be broken. Testing Lorentz invariance is therefore testing the foundation that everything else rests on. The November 2025 measurement set bounds on Lorentz invariance violation 10 times tighter than any previous bound. What that means physically is that if any deviation from perfect Lorentz invariance exists, it is smaller than 1 part in 10 to the very high powers that the measurement could resolve. For all practical and theoretical purposes, the invariance is exact. Some theories of quantum gravity, attempts to unify general relativity with quantum mechanics, predict that Lorentz invariance might break down at extremely small distance scales, far smaller than any current experiment can probe. This remains an active theoretical frontier, but at every scale currently testable, the invariance holds. The November 2025 result pushed that testable boundary further than ever. Every superluminal phenomenon documented to date, from the Tachyon dark vortices to Cherenkov radiation to quantum tunneling, operates within a framework that respects Lorentz invariance. The loopholes are not violations, they are permissions written into the framework itself. But there is one hypothetical entity that would, if it existed, genuinely violate the causality that Lorentz invariance protects. A particle that was born faster than light and can never slow down to it. A particle that travels backward in time relative to any slower observer. A particle that has never been found. In normal physics, particles are born at rest and can be accelerated. They can approach the speed of light but never reach it. The closer they get, the more energy it takes to push them faster. The speed of light is an asymptote, a limit they approach forever without arriving. A tachyon would be the opposite. A tachyon is a hypothetical particle born already above the speed of light. Its minimum speed is light speed itself. It can slow down toward light speed, but it can never slow further. Where ordinary matter approaches light speed from below and cannot cross it, a tachyon approaches light speed from above and cannot cross in the other direction. The mathematics of special relativity does allow for such particles in a narrow technical sense. The equations for how mass and velocity relate have a solution for particles with imaginary mass, a mass whose square is negative. Imaginary mass particles would behave exactly like tachyons, faster than light speed as their minimum, with speed increasing as energy decreases. Imaginary mass sounds like a made-up concept, but imaginary numbers are a real and productive part of mathematics, used throughout quantum mechanics and electrical engineering. The question is whether imaginary mass corresponds to anything physical. The problem with tachyons is causality. A tachyon moving faster than light relative to one observer would appear, to another observer moving at a different velocity, to be travelling backward in time. Send a tachyon signal from event A to event B faster than light, and some observers would see the signal arrive at B before it left A. The effect precedes the cause. This is called the causality paradox, or more informally, the tachyonic anti-telephone. If tachyons can carry information, they allow messages to be sent into the past. You could, in principle, receive your own instructions before you sent them, creating a loop with no beginning and no end. Logic collapses. No tachyon has ever been detected in any particle physics experiment. The searches have been extensive. High-energy particle colliders, cosmic ray detectors, and precision measurements of neutrino speeds have all produced null results. For decades, most physicists considered tachyons ruled out by experiment and deeply problematic in theory. A curiosity in the math with no physical reality. Then, in 2024, two physicists reopened the case. In 2024, physicists from the University of Warsaw and the University of Oxford published a paper in Physical Review D, arguing that the standard objections to tachyon existence were less airtight than the physics community had assumed. Their argument was precise. The standard reasoning goes like this. Tachyons violate causality because they can carry information faster than light, which allows signals to travel backward in time. Therefore, tachyons cannot exist. The Warsaw-Oxford paper examined the step from tachyons travel faster than light to tachyons can carry information faster than light, and argued that step was not as automatically justified as physicists had believed. The argument centered on whether tachyons, even if they existed, could actually be used to encode and transmit information. The authors pointed out that the physical behavior of tachyon fields in quantum field theory involves instabilities. The tachyon field does not settle into a stable state. It rolls away from its maximum toward a minimum, a process called tachyon condensation. During this condensation, the tachyon field evolves toward a different stable configuration that may not support information-carrying signals. This is highly technical. But the core claim is that tachyons might exist as physical entities while still being incapable of transmitting information at superluminal speeds, because the quantum field behavior prevents stable, controllable signal formation. If correct, a tachyon would join the list of phenomena that technically exceed the speed of light without enabling causality violation. A genuine faster-than-light particle, not carrying information, not breaking Einstein. The physics community has not accepted this as settled. It remains a theoretical proposal, published and peer-reviewed but contested. No experimental evidence for tachyons has been found, and most physicists consider their detection unlikely. The Warsaw-Oxford argument is considered interesting but unconfirmed. What makes it worth including in this story is what it reveals about the state of the field. Even the hardest conceptual limits in physics, the ones that seemed permanently closed, are still being examined, still being questioned, still being pushed. Every loophole investigated so far leads to the same structure. The speed of light is protected by something deeper than just a speed limit, and that something is what all of this has been building toward. Strip away all the technical language. Phase singularities, quantum tunneling, Lorentz invariance, tachyon condensation. Set it all aside for a moment. Here is what the speed of light is actually protecting. Cause before effect. That ordering. Cause before effect is the most basic feature of the universe we live in. Every experience you have ever had, every memory, every decision, every physical process rests on that sequence. Things happen because other things made them happen, and the making always comes first. If anything could carry information faster than light, that sequence could be violated. A receiver could get the message before it was sent. An explosion could destroy a lab before the experiment that caused it was run. You could, in principle, receive a warning about an event before the event occurred, act on that warning to prevent the event, and then have no reason to have received the warning. The universe prevents this. The speed of light is the speed at which cause and effect chains can propagate. It is the rate at which the universe processes its own history. Every apparent loophole works by staying on the right side of this boundary. Phase singularities carry no information, so they cannot build a causality-violating message. Quantum tunneling involves no spatial path, so the apparent superluminal velocity reflects no information transfer. Cosmic expansion carries no signal, only geometry. Cherenkov radiation is a byproduct of motion, not a controlled information channel. The shadow on the moon moves faster than light. but nothing on the left side of the moon can signal the right side using that shadow. There is no chain of causation that runs through the shadow from one point to another. Every single superluminal phenomenon confirmed to date obeys this same rule. The speed limit is never about preventing fast motion, it is about preventing backward causation. And nothing found so far, not the dark vortices, not tunneling, not the expanding universe, not the warp drive model, creates a mechanism for backward causation. Einstein understood this in 1905. The November 2025 measurement confirmed it to 10 times greater precision than ever before, and the Tachyon experiment in March 2026 demonstrated it again with one of the most visually striking examples yet. Darkness moved at infinite speed, and the universe kept its logic intact. The discovery the Tachyon made is not the end of something, it is the beginning of a new set of tools. And what those tools can now show us is as strange and important as everything that came before. Professor Kaminer described what his team's discovery actually enables in practical terms. The new electron interferometry technique, developed specifically for this experiment, achieves spatial resolution an order of magnitude below the polaritonic wavelength. Combined with femtosecond timing precision, it can image processes inside materials at spatial and temporal scales that were simply inaccessible before. That capability is the real prize. Superconductors are one immediate target. Superconductivity, the ability of certain materials to conduct electricity with zero resistance when cooled below a critical temperature, is one of the most valuable and least understood phenomena in materials physics. Inside a superconductor, electrons pair up and flow as a quantum fluid. Vortex structures similar to phase singularities appear in the magnetic field behavior of superconductors. Understanding how those vortices move, accelerate, and interact is directly tied to understanding why superconductivity works, and how to engineer materials that superconduct at higher temperatures. Higher temperature superconductors would transform energy transmission infrastructure. Power lines lose a significant fraction of their energy to resistance over long distances. Superconducting cables would lose essentially nothing. The technology that makes this possible requires understanding the nanoscale dynamics that the Tachyon experiment is now able to image directly. Biological chemistry is another application. Chemical reactions in living cells involve electron transfers, proton movements, and molecular vibrations that unfold on femtosecond timescales. Watching these processes in real time at the spatial resolution of individual molecules requires exactly the kind of ultrafast nanoscale imaging the Tachyon experiment pioneered. Direct observation of how proteins fold, how enzymes catalyze reactions, and how energy moves through biological systems could reshape biochemistry. Quantum information systems are a third area. Quantum computers use the quantum states of particles to store and process information. The coherence of those states, how long a quantum system maintains its quantum behavior before the environment disturbs it, is one of the central engineering challenges. Imaging the dynamics of quantum systems at femtosecond resolution could help identify the processes that destroy coherence and point toward materials or configurations that preserve it longer. The dark vortex experiment was described by Kaminer as revealing universal laws of nature shared by all types of waves. The electron interferometry method it required is now a tool that can be pointed at any wave system in nature. And the wave systems in nature include most of the processes that drive biology, chemistry, energy technology, and computing. The speed record is the headline. The method is the legacy. The Tachyon experiment took place inside a crystal flake thinner than a hair, but the phenomenon it studied is everywhere. Phase singularities, dark points surrounded by swirling vortex structures, appear in every wave system in nature. The mathematics that governs them in light also governs them in sound, in water, in quantum fields, in plasma, in the collective behavior of atoms cooled to near absolute zero. Ocean currents carry vortices. A hurricane is a singularity in the velocity field of the atmosphere, a point around which the wind direction swirls continuously. The eye of the hurricane is the singularity itself, a region of near calm surrounded by the rotating structure. In quantum matter, phase singularities appear in superfluids. A superfluid is a state of matter typically achieved by cooling helium to just above absolute zero, where quantum effects become dominant and the fluid flows without friction or viscosity. Superfluid helium forms quantum vortices, tiny rotating structures with phase singularities at their cores. These are not analogies. They are mathematically identical to the optical vortices in the tachyon experiment. Superconductors, as discussed earlier, contain magnetic vortices with the same topological structure. Each vortex carries exactly one quantum of magnetic flux, a value set by fundamental constants. The dynamics of these vortices, how they move under an applied current, how they interact with each other, how they pin to defects in the crystal, directly control the material's superconducting properties. Even the human voice contains phase singularities. The acoustic wave pattern produced by a person speaking in a room with reflections includes points where the amplitude drops to zero and the phase swirls. Engineers working on noise-cancelling systems and acoustic design encounter these structures routinely. What the tachyon experiment revealed is how singularities behave in their most extreme state, the moment just before mutual annihilation. That behaviour, the exponential acceleration, the formerly infinite velocity, the simultaneous disappearance, turns out to be universal. Every wave system that supports singularities should display the same dynamics under the same conditions. The experiment was conducted in light because that is where the theoretical prediction originated and where the tools to test it were most advanced. But the results apply everywhere. Every superfluid quantum vortex approaching annihilation should accelerate the same way. Every acoustic singularity in a collapsing wave pattern should hit the same formally superluminal velocity. The universe uses the same playbook for waves regardless of what the waves are made of, and at the extreme edge of that playbook, where two singularities close in on each other and geometry takes over from physics, the rules bend in the same direction every time. There is one more question that the tachyon discovery left explicitly unanswered, and it is the one that, if answered differently than expected, would change everything. The reason the dark vortices do not violate Einstein is clear. They carry no information. Their motion is a geometric property of the wave, and geometric features cannot be controlled or modulated in a way that encodes a message. That reasoning depends on a boundary, a distinction between wave features that carry information and wave features that do not. And that boundary, while well established in current physics, is the subject of active research. The question is precise. Phase singularities are defined as points of zero amplitude and undefined phase. They exist because of wave interference, and their positions are determined by the overall pattern of the interfering waves. In the current framework, the singularity's position cannot be controlled independently of the whole wave pattern, and the whole wave pattern cannot be modulated fast enough, in the right way, to encode information in the singularity's motion alone. But wave physics is not fully explored. The tachyon team acknowledged in their published paper that extending the experiment to three-dimensional systems, to more complex material configurations, and to ensembles of many singularities interacting simultaneously is the next major research direction. In 3 dimensions, singularity behavior becomes richer. Topological structures that are stable in 2 dimensions can evolve differently when extended into a third. Ensembles of many singularities interacting might display collective behaviors not seen in the 2 singularity case the experiment studied. The theoretical question is whether any configuration of singularity behavior could constitute an information channel. The current answer is no, based on the fundamental definitions of what a singularity is and what information transfer requires. But the exact mathematical boundary between information-bearing and non-information-bearing wave features is an active area of investigation. If anyone found a way to encode a controlled signal in the motion of a singularity ensemble, the information speed limit would face a genuine challenge. The current theoretical framework says this is impossible by definition. But 50 years ago, the theoretical framework said dark vortices moving faster than light was a footnote nobody could test. Definitions in physics sometimes turn out to be descriptions of what we have studied so far rather than absolute constraints on what is possible. The Technion team did not claim any threat to the information speed limit. They were explicit that no information was transmitted superluminally in their experiment, but they also identified the three-dimensional extension and the multi-singularity ensemble as open problems. Science does not announce conclusions it has not reached, and that honesty is what makes this the right place to close in on what all of this actually means. Start at the beginning of this story. A team of physicists watched darkness move at infinite speed inside a crystal flake. Confirmed, published, March 2026, and Einstein's rules were untouched. Every chapter of this story followed the same structure. Something exceeded the speed of light. And then careful analysis revealed that the thing moving was not a thing at all. Geometric feature, a wave pattern, an intersection, a probability cloud, the expanding space between galaxies, a topological abstraction in a crystal. The universe has one rule: cause comes before effect, and the speed of light is the rate at which causes can reach effects. Anything that travels slower than that rate cannot violate causality. Anything that travels faster, if it carries no information, no energy, no mass, also cannot violate causality because it has nothing to deliver. The dark vortices confirm this from a new angle. A laser dot on the moon confirmed it from a simple one. Cherenkov radiation confirmed it visibly, glowing blue in reactors around the world. Quantum tunneling confirmed it through the strange route of quantum non-spatiality. The expanding universe confirmed it on the larger scale that exists. And the November 2025 precision test confirmed, to 10 times greater accuracy than any previous measurement, that the framework holding all of this together is correct. The warp drive research added something different. It showed that space-time curvature, previously considered the domain of exotic theoretical speculation, can be produced using real matter and real energy. The physics community now has a physically realizable warp model, subluminal, enormous in energy requirements, but grounded in known science. The path from there to faster-than-light travel is not mapped, but the first confirmed step onto that path has been taken. The tachyon question remains open at the theoretical edge, contested, unconfirmed, and probing the deepest assumptions about what relativity actually forbids. And the Technion electron interferometry technique, built to prove a 50-year-old prediction, is now a tool pointed at superconductors, biological chemistry, quantum information systems, and every wave system in nature that was previously too fast and too small to see. One experiment, one dark point, 3 quadrillionths of a second. And the universe revealed something it had been keeping since the 1970s. The speed limit is real, the loopholes are real, and the boundary between them is one of the most precisely understood edges in all of physics. The rule was never nothing moves faster than light. The rule was always nothing carrying information, mass or energy can exceed the speed of causality, and the universe, tested to unprecedented precision, obeys that rule without exception. Every loophole confirms the same thing. The law is not a wall with cracks, it is an architecture. And the more carefully we look at it, the more precisely it holds. The universe is stranger than it looks from the outside, and it is far more exact than it has any right to be.